Hello, good afternoon, bonjour. So my name is Tara Gopnath. I work with the Linux Systems Group at Microsoft. I work on virtualization and security, which is the topic of my talk today. Prior to this, I used to work in the embedded power management ecosystem. I did work a lot on, I used to do a lot of power management and thermal management drivers, and I used to maintain the Qualcomm thermal drivers and the Qualcomm crypto drivers. And today I'm here to talk about Linux Virtualization Based Security, which is a feature that my team and I have been working on for the last 2 to 3 years now. Okay, so what is Linux Virtualization Based Security? It's a term that we have coined, and it is meant to depict how we can enhance the security of a VM or a host in certain cases by establishing a higher privileged trusted environment within the VM or the host by leveraging the hypervisor security boundary. And once this trusted environment is established, what we can do with it is to protect the integrity of certain critical operating system resources like memory, keys, registers, etc. Prevent bypassing of existing security policies and mechanisms by malicious kernel attackers, and also support a trusted execution environment wherein you can provide some secure services to the VM or to the host. It's really what I'm going to talk about here is all on a layered security approach, where what we are trying to say is that even if your kernel is compromised, we can improve the security or we can protect the kernel, critical kernel resources through hypervisor or through virtualization. So why did we start this project? What was the motivation? So 2 main reasons. One is that there are increasing amount of kernel vulnerabilities that we hear about out there, and user space can actually exploit these vulnerabilities and gain access to kernel. And once somebody gains access to kernel, all the kernel self-protection mechanisms are down, and so they can access the critical resources. So this is a paper actually, in the link here is a paper that was written in 2024. It's a nice one, it's a long one. It's called a slubstick attack. And at the end of it, the attacker can actually gain access to kernel, to page tables, and depending on what they get access to, they can even go ahead and modify the kernel text. And the other motivation was that there are proprietary solutions out there that do leverage this hypervisor kernel boundary to enforce or to provide system security. And we did want to come up with a mainline approach and improve the security posture of mainline Linux, basically. So the features that we are targeting with LVBS can be broadly classified into 2 buckets. The first one is kernel hardening and kernel integrity. By that, what I mean is that to enforce critical kernel resource protection from outside the guest or host kernel. And by resources here, I really mean critical kernel registers and entire kernel memory, text, data, read-only data, the vmalloc space, everything, the entire kernel memory. So through this higher privilege environment that we can establish, it can actually monitor the registers and raise exceptions in case of someone tampering with critical registers. It can also enforce the read-execute permissions and read-only, the write-execute permissions and read-only permissions that are set in the kernel memory space. And again, raise exceptions in case of violation. And the second thing we can do through this feature is to improve kernel integrity. And that is, okay, so when I say kernel integrity again, so it means 1 is to prevent attempts at disabling the set protections. 2 is making sure that only authenticated modules or authenticated features can be allowed to modify these protections. So it's really defense in depth. Kernel today does have self-protection mechanisms. Modules are authenticated. But what we are talking about here is defense in depth, where we are saying that a part of this can be moved outside the kernel into a higher privileged environment from where it can be handled. And the second use case that we envision with this is to support secure enclaves. And for this, we envision establishing a trusted execution environment wherein certain trusted applications can run, and it can provide secure services to the operating system. It is very similar to the trust zone that exists in ARM world. And use cases for secure enclaves includes things like secure logging, secure key management, credential management, virtual hardware security module, etc. So before we move on, I want to talk a little bit on the threat model. So here, again, like I said, the goal is to protect the kernel from a user space attacker who is exploiting a kernel vulnerability and gains access into the kernel. And for this, for the whole design and architecture that we have developed so far, we do assume that at boot, kernel is benign. And whatever boot verification mechanism, whether it is secure boot or something else that one has implemented, can be trusted. And we say that the kernel can be trusted till the first verified or till the first user space process starts running, which is the init. Till that point, the kernel is verified and kernel can be trusted. And after that, we assume that the kernel can be compromised, and which is where the LVBS should kick in and say that these are the protections that we have established, and if you violate, we will raise an exception. So again, the TCB for LVBS in a non-confidential computing scenario does include hypervisor, host OS, and the hardware. All these three are within the TCB. So a little bit on the architecture. Like I said, and when we started this, we did not want to do a proprietary solution. We want to make this the mainline solution for Linux security. So we do envision a hypervisor and platform agnostic approach here. And we would like, the way we have at least attempted to design and architect this is in such a manner that it can interact with any hypervisor, whether it is Hyper-V, whether it's KVM or anything else, right, that exists there. Similarly, these are some of the technologies that exist today to create these separate privileged environments within a VM. So Hyper-V has something known as virtual trust levels, which is a software-based mechanism. And then AMD, through their confidential hardware, supports virtual machine privilege levels. Intel supports TD partitions, and ARM has CCA planes. These are all the technologies that are out there today. And we would like the solution to work across all this, eventually at least. So again, so there are a few key hardware requirements to support this. One is the availability of second level address translation, which is in Intel, Intel it is known as EPT, AMD calls it RVI, ARM calls it stage 2 page table. So basically, what it provides is a secondary complementary layer of memory permissions that can only be controlled by this higher privileged environment. And the other hardware feature that we require is the ability to differentiate between kernel and user execute modes, or MBEC. So, on the architecture front, right, I did talk about two use cases that we envision. One is the kernel integrity and kernel hardening, and the other one is secure enclaves. Now, to support kernel integrity, this is our proposal on how we can. This is one way of supporting it. I'm not saying this is the best way. This is something we have already sent two RFCs to the community, but we are very, very open to coming up with any other way. So what we envision here is developing a very light agnostic abstraction layer known as hypervisor enforced kernel integrity layer, or HECI. It is nothing but a pass-through layer. It will have APIs that kernel frameworks can call into, and it will be hypervisor agnostic, platform agnostic, and it will also provide hooks for the hypervisor driver to hook into, which can then be further called to invoke services from this trusted execution environment. Again, a very simple pass-through layer. It really does not have any major logic there other than carrying the control commands from one side to the other side. That's it. So these are the few APIs. Again, we did send out RFC on this in the community. So the main one here is HECI late init, which is called during late boot of the kernel after kernel has implemented its own set of protection. And what it tells the privileged environment to do is it tells it that, okay, the boot is done. User space process is about to start running. So lock in all my registers. If anyone attempts to change it, raise an exception. Enforce all the kernel memory permissions that have been set so far on the kernel memory in the second level address translation table, and also mark that this is the end of boot. And then rest of the APIs here is all for kernel to call during various features that it supports that involves text patching. So HECI validate module and HECI free module in it is called during module loading. So HECI validate module is to validate and authenticate the module in this trusted execution environment, and HECI free module in it is to actually release the memory permissions of module init after module init has been called, so that the space can be reused for other purposes. Oh yeah, sure.
So you said that the kernel can be trusted until it boots.
Yes.
And then after that, it cannot be trusted, right?
Right.
But it looks like at least some of these functions are things that you can call after the kernel is not trusted anymore. So how does that work?
So late init is called before that point. It is before the init process starts running. It is once the kernel sets its protections.
So the protections are set
at then.
Okay.
And after that point, two things that happen is, one is the execution environment can relax the protections and write or set the memory protections to, let's say, execute for a write memory region or vice versa, however you want to do it, but only after authentication of that request. And by it can be different kinds of authentication. For module, it can be signature verification and checking of the actual memory content. For text patching, it can be checking where that request is coming from, things like that.
Is there a way any of that can be bypassed, or any of those checks after the kernel is not trusted?
That's a good question. So what we are saying, so it's like a chicken and egg problem there, right? Because you have kernel code section where these hooks exist and where these API calls are put in. And that is protected at boot. So what we are saying is, once that is protected, that can no longer be written into. So hence those checks cannot be bypassed. But if there is a way that can happen, yes, then.
Okay.
Yeah, it's kind of a circular problem that you're talking about.
Yeah.
Yeah.
Okay, thanks.
Okay, so where was I? Yes, so HECI text poke, that was a very, very controversial API that we sent, because what it does is actually during text poke, which goes and patches the text to support various features like jump label optimization, static call optimization, ftrace, and makes the call into the hypervisor to enable that or to relax permissions. So we need to really, really discuss that on how to support it. There are strong opinions about it. I'll leave it at that. And then there are the key APIs, which is to basically send secondary keys after boot if needed, into the privileged world, and also the blacklist hashes. The initial set of keys are all sent along with late init, basically. So the second feature I talked about, supporting secure enclaves. We really did not need to invent anything for it. It already existed in the kernel thanks to ARM ecosystem and trust zone. Opti. So this is the picture of how Opti looks like today, or the Opti interfaces looks like today. And to support secure enclaves with LVBS, only two things needed to change. One is the communication between the Linux Opti kernel driver to the Opti OS, which is SMC based today. That has to be changed to support whatever calls into whatever platforms that I talked about earlier. And the second one is Opti OS itself that runs in the secure world, supports only ARM. It needs to support x64. Once these two, we have actually done a prototype of this, and once these two happen, Opti works as is to support secure enclaves with any environment. And why we decided on Opti was because it already has a very well-defined, well-documented interface. There is a very active developer community around it. It is actively maintained. There are a lot of public TAs available which can be reused. And the client and the trusted application APIs are all adhere to the global platform API specification. So we really think that to support secure enclaves, Opti is the best. Okay, with that, because we are interested in Hyper-V being Microsoft, I will talk for a few slides on that. Okay, so this is how Hyper-V provides this support for hosting the separate execution environment. Hyper-V has a mode called virtual secure mode, and through it, it enables something known as virtual trust levels, which are these separate execution environments. They are software abstractions, basically. And theoretically, we can support up to 16 such execution environments. For practical purposes, it is 3. For the purpose of this talk, it is only 2, VTL 0 and VTL 1. VTL 0 is where the normal operating system operates or runs, and VTL 1 is this higher privileged trusted execution environment. And higher the level of a VTL, the more privileges it has. A higher VTL always has higher privilege over a low VTL, over a lower VTL, and any memory permissions that are set by a higher VTL takes precedence over the memory permissions set by a lower VTL at the second level address table level, second level page table level. And if anyone is more interested to learn about it, there is a link there, and there is a lot of other information on VBS, virtual secure mode itself. And how the transition between the VTL 0 to VTL 1 happens is through VTL call and VTL return. There are 2 kinds of interactions that are possible. One is synchronous, the other one is asynchronous. In a synchronous transition, the VTL 0 explicitly makes a call into VTL 1, and the VTL 1 explicitly returns back. In asynchronous is an interrupt-based entry mechanism where a CPU executing in the lower privileged environment of VTL 0 enters VTL 1 because there is an interrupt pending in VTL 1, and exit is always explicit return. So an interrupt in VTL 0 cannot take a CPU away from VTL 1, and this is actually different from trust zone, whereas in trust zone this is possible. So now let's talk about secure kernel. There is a privileged environment. So what do we run there? We did an analysis, and ideally it has to be something that has a really small TCP, minimum dependency, memory safe, ability to support these secure interfaces, to support trusted applications, maintainable, and all that, right? And we evaluated a bunch of candidates. Initially, when we started this program, and for almost a year and a half, or even 2 years, still very recently, we were running minimal Linux kernel in secure world. And minimal Linux kernel is really not ideal to run as a secure OS because no matter however much you try, the TCP is still large. There are interfaces, no matter how much you lock it down. B, there is a scheduler running. Removing scheduler is impossible in Linux. And we did do a few things to do that. And remove that is stopping tick, RCU, and removing scheduling. There are people in this room who will not at all be happy on all the things we had to do for that. And I can talk for 40 minutes on another 40 minutes on what I did for that. So that's not topic for this conversation, but that is what happened. So it is not minimal Linux kernel. We did check Opti out. Again, Opti only has support for ARM. Opti does not have support for x64 today. And it's a very, very interesting and very, very compelling candidate, actually. If Opti has x64 support, there's very few reasons not to choose Opti at this point. Other than Opti is probably written in C, and we are moving towards more memory-safe languages of late, but yeah. Coconut SVSM is a Rust-based secure OS that is being developed for confidential computing purposes. We did talk to some of the people who are involved with Coconut SVSM, and the feedback we got was that at least now it is not mature enough for us to enable LVB or support LVBS through it because it doesn't give us all the interfaces needed, especially around memory and maybe a little bit of timers and things like that. And so finally, what we are doing is a Rust-based minimal firmware that runs in secure OS for us. Like I said, it is internally being developed now, and it is an internal, it is not yet open source, but we do envision to open source it. It's not like we don't intend to keep it proprietary at all. So with that, I will not talk much on this picture. This is how a system, the Hyper-V system looks like, putting all this together at this point. So there are two, within a guest or within a host, we can support this on host also. So within a VM, there are two partitions, a VTL 0 and a VTL 1. And VTL 0 is where normal operating system runs. VTL 1 is where the privileged environment. And VTL 0 and the user side runs the T-client API library, and there are applications running there which can talk through Opti driver into it and can interact with VTL1. And VTL1, the Rust secure kernel, actually provides boot services, Opti interface, and HECI services. And the Opti interface running in the secure OS actually calls into the trusted application. Okay, so I want to actually talk a bit on this. Where do we stand with KVM, right? So when we initially started this effort, let me rewind. Like I said, all we care about here is that the kernel should be protected from outside, from a higher privileged entity. Purely from a VM perspective, host is a higher privileged entity. Now, KVM has a problem where KVM does not support enabling of different privilege levels for a CPU. Inherently, KVM does not have that support. So when we started, we said that, okay, considering KVM does not have the support, why don't we try to implement this for VMs through host, at least some pieces of it, because host is a higher privilege environment as far as a VM is concerned. And on that front, we did send out a few RFCs. The RFC had the HECI APIs that I talked about. It obviously had the KVM driver that will interact with HECI, and also had some KVM changes at the KVM layer itself to support one MBEC. MBEC support is missing in KVM, and also to support some of the restrictions, right? The permission restriction and things like that. Parallelly, we had an effort happening from Amazon where they wanted to enable or emulate Hyper-V's VTLs in KVM. Okay, they are not competing features, or they are not competing offerings, but they were all parallel. They were happening parallelly, and it was interesting. And the feedback we got from the community, from KVM maintainers, was that we really do not want these features to be enabled in the host KVM. We do want it to happen outside of it. So they were actually encouraging Amazon's solution of establishing secure, separate privileged environments through KVM. But like I started off saying this, KVM does not inherently support it. So right now, we have a RFC from Paulo, who is the maintainer of KVM, one of the maintainers of KVM, on something known as VM planes, which is a backend, which is a proposal for a backend or a tech plumbing piece to support separate privileged execution environment for a CPU within KVM. And he has explained it much better than what I have in his RFC. So he also envisions using VM planes to host different kinds of privileged execution environments, whether it is Hyper-V's VTL, whether it is AMD's VMPLs, or Intel's TD partitions, or whatever that is. And so that is where we stand with that today. And that actually brings me to my next slide. It states, we are actually looking for collaboration on that front. We do not think that HECI should be applicable only to Hyper-V. HECI, we think, should be applicable across mainline Linux. We think it should work with KVM. And for that, it is very, very important that KVM supports VM planes, and we can actually host separate privileged environments with KVM. So we are looking for collaboration there, either by reviewing or even implementing some of these privileged environments and things like that. The code for HECI and the Hyper-V systems itself is there in this GitHub. We are planning to send up RFCs. We welcome any kind of review, any kind of interaction with this. We are very much open for collaboration here. And finally, I think it will be a very interesting project if Opti supports x64. We do not have the bandwidth to do it by ourselves, but we are more than willing to collaborate on it. And I really think it has potential. That actually brings me to my last slide, which is QA. But before that, very often when I talk about it, I do get this question. With confidential computing, how is LVBS relevant? And I did take the liberty of putting this slide together for that, answering that question. And in my opinion, confidential computing and LVBS are not competing technologies. They are orthogonal and they are complementary technologies to each other. So what I have here on the left is the TCB of a confidential VM. No LVBS, just a confidential VM. So if you look here, the hypervisor is out of TCB, host is outside of TCB. But the hardware and the entire user and kernel space in a confidential VM is within the TCB. The second picture here is a TCB on a VM with LVBS, no confidential hardware. So in this case, the Hyper-V, host, hardware, everything is within the TCB, but on the VM side itself, the normal operating system is outside the TCB, and only the secure world is within the TCB. And ideally, I think we should move towards a world where there is confidential VM and LVBS together, in which case, hypervisor and host is outside TCB, and within the VM, the normal world or the regular operating system is also outside this TCB. And this is why I think that they are complementary technologies and they are not competing technology at all. That brings me to QA.
I think I can imagine how useful it is for like big cloud providers, but like, do you see where it can be useful in other environments?
You mean without a hypervisor and without in a non-virtualized environment?
Yeah, no, it's kind of generic use case.
Not really, because in a non-virtualized environment, we already have ARMS trust zone for embedded ecosystem. So and we are actually talking about, it really depends. If you are able to create a separate execution environment for a CPU, yes, it is useful. Mm-hmm. But I do not know of a technology where that is possible today.
Thanks.
Yeah.
Yeah, it was just like a comment, like it could be like any hardening hardware you want to implement. And like the most popular one is like a game console that use this kind of stuff as well. Or they implement the kind of booting or hardening, don't trust anything afterwards.
I'm sorry, I cannot hear you well.
Yeah, okay, sorry.
Yeah.
I'm saying just like the kind of application that has been used widely is like console games. Game console, where hardening the kernel is done very early with crypto keys and stuff. It's kind of the same way when everything is done before the init and you cannot trust the kernel afterwards. It's not really a question. No? It's like
oh, okay. Okay.
Do you know if there are any equivalents for RISC-V systems or not yet?
That's a good question. I do not know the answer to that. I can look it up, but yeah, sorry.
So I actually, when you started introducing what it was you were going to be talking about, I thought you were going to say, and so we've embedded a hypervisor inside the kernel, and so you can use this on your laptop. And that's not totally not what you were talking about. But would that be an interest? I mean, people were talking about, you know, is this more? Can we do anything in a non-hypervisor environment?
Right.
Do you think that would be an interesting thing to do?
You mean to have a hypervisor within the kernel, so that? But then that would be like a KVM host trying to protect itself through KVM, right? Won't it? Because
I think it might be more secure than.
But yes, so let me put it this way. Even in that, are you talking about protecting hypervisor within a kernel and protecting itself?
I'm talking about putting a hypervisor inside the kernel, and then at boot time you had that late init call. At that late init call, the hypervisor would then take itself off, seal itself off and seal up the kernel nice and tight around it so that it can't be affected, and it can do the protection parts of what you were talking about.
But then the hypervisor is running at the kernel level in that case.
Right, yes.
Yes, so it is essentially kernel self-protection then, right?
Yeah, yeah.
Yeah. So,
So following up a bit on Matthew's question there, because I think they're doing Matthew's idea. Have you looked at what the Android people have been doing with protected KVM on ARM64, where they run the hypervisor at the hypervisor level and run the kernel at guest level?
we have not fully looked at PKVM. We know that PKVM exists, and it is not fully mainline, we know that. So, and then there was VM planes. We have been talking with KVM folks, and the recommendation has been VM planes, and to move towards that. So that is what we have been focusing on, at least.
Yeah, I just want to say it's not just ARM. x86 is now, we're working on it too. So, yeah, for
but we are
Chromebooks.
open to any technology through KVM. We can if we can support this execution environments, we are open to it.
The
It
idea
doesn't
of like
matter.
PKVM, like for Chromebooks, is for basically to put a secure place for like your fingerprint reader, have code like, so they'll be handling that. Whoops, I wasn't sure if you could still hear me. Okay, so yeah, that's the purpose for of like our laptops, is like for security and things for like your fingerprint printer, fingerprint reader and such like that will be in a secured form.
Yeah.
And exactly that's what it does. It kind of like the hypervisor takes over, and the Linux kernel is just a
Yeah.
guest.
So yes, it is applicable in that environment, yes. So we have not studied it, yeah.
Thank you.
Thank you very much.